Today I am going to present some of the recent work entitled as Novel and Facile Solution Group for large-scale selective well-aligned zinc oxide nanorods on zinc oxide silicon substrate, structural, optical, and field emission profiles. I belong to Chumphon National University. I am doing PhD under the guidance of Professor Reddy. As we know, zinc oxide is a wide-band and facile material which has a large excited binding energy, nearly 60 milli-electron volts. So, due to this, it has a wide variety of applications in different emerging and diverging fields, like the optoelectronic devices, transparent electrodes, photonic crystals and photonic devices, transducers, chemical, bio and gas sensors, light emitting diodes, solar energy materials, and after the titanium, zinc oxide is recognized as the best photocatalyst. I would like to introduce the very simple and facile solution route which makes advantage over various methods like chemical vapor deposition, MOCVD, MV, and pulsar laser deposition, etc. The method is templateless and surfactant-free. Through this method, there is a possibility of large-scale fabrication of on a wafer scale by low cost and low low temperature. A very simple and easy technique, less hazardous, very famous for chemical etching and especially for wet chemical etching, catalyst-free and environmentally friendly technique. This is the experimental method how we prepare our zinc oxide aligned nanorods, just to mix the HMTA with zinc nitrate and stir for some time and refluxing at a temperature between 70 to 110. Finally, we are cleaning the substrate and drying. Here, this diagram presents the schematic view of selectively grown zinc oxide nanorods. First, we coat zinc oxide silicon substrate with zinc oxide layer, and upon PR spin coating, we use positive PR. And finally, we are using the ICP inductive co-bleaching, or it's called as a dry etching, to pattern the substrate for growth of zinc oxide nanorods on selective positions. This figure presents the general morphology of FSM images of selectively grown zinc oxide nanorods on a scale pattern. Each nanorod has about the diameter between 50 to 60 nanometers and their length from 600 to 700 nanometers. The next figure, which presents this, we chosen here two types of patterns by using the very simple mask, polymer mask as a substrate. As a masking material, a soft mask, and it's very cheap as compared to metal chrome mask to pattern the substrate. So we use two types of pattern, like circular and square shape, to obtain the zinc oxide nanorods on selective positions. This chemical conformation we have done of zinc oxide nanorods using the EDX, which shows that these zinc oxide nanorods are completely composed of zinc and oxygen. The silicon substrate peak appears due to the substrate. The XRD diffraction pattern confirms that these zinc oxide nanorods are single crystalline because it shows the 002 intensity, high intensity 002 peak, which confirms that they are well oriented on the substrate and grown along the C-axis direction. Further structural conformation is done by doing the T and transmission electron microscopy, which shows that these zinc oxide nanorods are single crystalline in nature. Finally, we have done the photoluminescence, room temperature photoluminescence measurement. As I said before, that we are using the zinc oxide, silicon coated zinc oxide film. So we have performed the photoluminescence measurement at room temperature for zinc oxide film and zinc oxide nanorods as well. We observe the UV emission is much 3 or 4-fold higher than as compared with the zinc oxide film, which suggests that the ongoing zinc oxide nanorods on selectively positions enhance the UV emission. Further device application is done by doing the field emission FUD device. We have used the sample silicon zinc oxide coated silicon substrate and the top electrode is I2 phosphor-coated I2 glass substrate to construct the field emission device, which shows the low turn on field, which is 2.85, and which the FN plot is just a linear plot. We have compared our data, this data with the recent published by other people on the zinc oxide group by Shin et al. In advanced material last year. They are showing the current density is equal to 10 microampere centimeter inverse, but we have achieved a good current density, which is 0.52 milliampere centimeter square, and a very low turn on field using a very simple and a novel solution technique, which suggests that these zinc oxide nanorods can be a good candidate for the field emission devices. This is a uniform fluorescence image during the field emission. When we apply the current, we can see this is before the substrate, the area we captured before the device measurement of device performance, and after during the measurement, we find the fluorescence image, the uniform fluorescence image of in these spots, which shows that these zinc oxide nanorods can be a very good candidate for the field emission device. Finally, I would like to conclude my talk. We have successfully grown the zinc oxide nanorods around the 56 nanometer diameter, and the length is near about 600 to 700 nanometers. The SAD analysis is consistent with the XRD, which confirms that the single-phase plane nature with the woodside hexagonal phase. These nanorods showed very good optical properties with less structural defects. The common strategy is simple processing and fine quality makes this material this route very attractive and significant. Finally, I would like to say that the field emission properties of the zinc oxide nanorods show very high beta values, low turn on field, and a large emission efficiency. I would like to acknowledge this Ministry of Education and Human Resource Development BK21 program and Korean Science and Engineering Foundation COSEF. I'm deeply indebted to my worthy Professor Wai Han for his involved intellectual and economical supports to continue my study. I personally would like to acknowledge Dr. Reddy for useful discussions and moral support, and I would like to express my gratitude to all of my lab members, Mr. YK Park, SHK, GHK, and members. Thank you very much.
Thank you.